Section 12.3, the dot product. So in previous videos, we've talked about how to add vectors together, vector addition. We introduced the concept of scalars and said how to multiply a vector by a scalar multiplication. But we also said we don't yet have a way to multiply two vectors together. And so there's actually going to be a couple ways to do this. The dot product is going to be our first way to multiply two vectors together. Here's some learning goals. So you should know the definition, you should know the properties of a dot product, you should be able to calculate dot products. We'll also talk about connections between the dot products and angles between vectors. And at the end, we'll talk about projections and components. Okay, so what is the dot product? Our first way to multiply vectors together here. So first off, notation is going to be u dot v. It is perhaps meaningful for me before I give a example of this to emphasize when we're doing multiplication of, say, if I asked you to multiply m and n together, where those are numbers, you might write m times n, you might write m dot m, you might write m. You might just leave a space to mean multiplication, you might use a dot, you might use a cross, a times symbol. When we're doing dot products, it's very important that you put the dot. If you just write u, v next to each other to mean the dot product, that's not good notation. Please don't do that. Okay, what is the dot product? So let me just do definition with example here. Let's suppose that I have a vector 1, 3, 5. I want to take the dot product of that with the vector 2, 4, 6. So note these are vectors each with 3 components here. How I compute the dot product is that I do the first entry of the first vector times the first entry of the second vector plus the second entry of the first vector times the second entry of the second vector plus the third entry of the first vector times the third entry of the second vector. So 1 times 2 plus 3 times 4 plus 5 times 6. So this is how we compute the dot product. You multiply together the corresponding entries in the two vectors, and each of those products, you add them up. Okay, so this is the dot product here. I should say it also works in other dimensions. So for example, we just had 2-dimensional vectors. I want to do 1, 7 dot product -2, 6. This would be 1 times -2 plus 7 times 6. So this is a dot product. In other math classes, we can extend to more than 3 dimensions, 4, 5, or 6 or more dimensions, and it works in the same way. Just multiply the corresponding entries together and add up all of those products. Okay, so let's talk about some dot product properties here. Let me point out, for instance, so what happens if we were to do, 246.135. So that is, we're just interchanging these two vectors here. And we get 2 times 1 plus 4 times 3 plus 6 times 5. And that's going to be, since ordinary multiplication of real numbers is commutative, this is going to be the same thing. So this shows us that u dot v is equal to v dot u. So the dot product is commutative. Okay, so another thing that is worth doing here is what happens if we take a dot product of a vector with itself. So if we have V is, let's just take 1, 3, 5. And we do V dot V. So that would be 1, 3, 5 dot 1, 3, 5. We would end up with 1 times 1 plus 3 times 3 plus 5 times 5. Or I could write that as 1 squared plus 3 squared plus 5 squared. So question, take a moment to think. Does this look like anything that we've done previously? What happens if I were to ask you to compute the length of V, the magnitude of V? So if we just find the length of the vector 1, 3, 5, we square the components, and we sum up those squares, and then take the square root. So what's the difference between this and this? This is just the square root of this. This is the square of this. So conclusion, how do these relate to each other? V dot V is equal to the length of V squared. This is a common little trick. Okay, couple other rules to throw into this video here. If you have the 0 vector dot product with any vector in either order, dot product is commutative, is 0. So it's important to write the 0 vector, the vector sign here, because this is 0 the vector, this is 0 the number, the scalar. And a few more rules here. For any scalar lambda, lambda v dot w is equal to lambda times v dot w. And then we have a distributive law. If we take vectors v and w, add them together, and then do u dotted with that, we could have just done u dot v plus u dot w. So a distributive law. Okay, so this is an introduction to the dot product.